Welcome, everybody. Thank you for joining us on this busy day or week, 2 weeks after COP. I'm sure everybody's tiring of seminars and so on, but I'm very grateful that we still have a decent turnout, and I hope you enjoy tonight's presentations about the finer arts, I suppose, expert design, installation and maintenance of systems, both solar thermal, solar PV, and presentation on the Bullet Center, which is a living building certified building, and how it performs in real life. So without further ado, I'd like to invite Dan Gates, who's the principal engineer of Flow Surfaces, CIBSE qualified engineer, to talk through solar thermal installations, design installations and maintenance issues, and what to watch out for and what's best to match up with and other heat sources, etc. Over to you, Dan.
Great, thanks, Glo. I'll try and share the screen. Hopefully you can see that and everyone can hear me. Yeah, my name's Dan Gates. I'm the engineer at Flow Services. So we're sustainable building service engineers. So we cover energy assessors. We do HVAC M&E design and a lot of renewable energy, net zero technology assessments. So a few projects that we've worked on, that's Mary Arnold Foster. We do quite a bit of work with her. And then there's a new passive house in Dundee that was on the cover of Passive House magazine recently. And at the other end of the scale, this is Plymouth University, working with Kenza Contracting on that in the summer. It's one of England's biggest public sector ground source heat pump project, but I put that in because there's some solar PV on the roof there as well. Trying to work out the slides. I think in terms of heating, solar's obviously got a lot, solar PV's got a lot to do with electricity, but heating's going to be more and more important. This pie chart here is the UK emissions, of which 30% are from buildings, and you can see 23% is from heating. So 84% of UK is on gas, central heating, burning natural gas, and there's a large carbon footprint here. At the same time, the grid is decarbonising. So this chart down on the right-hand side, from 2010, when the SAP was initiated, we had electricity at 500 grams kilowatt hour, and then over time, over the last 10 years, it's come right down. So now we've got at the level that the grid is under gas. So electric heating is better than gas in terms of carbon. And then if you use a heat pump, you can see the factors here. Typical heat pump, probably 2 to 3. You're down under 100 grams per carbon for your heating. This graph on the left is showing the electricity. So I've put a yellow line along here. So that's the contribution from offshore wind at the moment. In 2021 is at 10 gigawatts. But by 2030, we'll be up at close to 40, maybe 50 gigawatts of offshore wind. And this red line here that goes up and down during the day, that's electricity. So you can see a lot of the electricity is being covered, and potentially could all go renewable, the whole grid to be virtually decarbonized. But then you've got these massive energy demands here moving up and down, and that's the gas, so that's heating, and it's very peaky. So you get a massive peak in the morning, massive peak in the afternoon. And then in that context, we're looking at, this a graph might be familiar to some of us on Twitter, but this is a heating curve. So on the axis up here, we've got heating system, flow temperatures, and then on the x-axis down here, we've got outside temperatures. So generally a heating system in Glasgow is designed at -4, -5, and you're trying to set the system to cope with those temperatures. But because we've undersized systems and typically not done much design in the UK, we've been coping with it by just running everything at very hot temperatures, 75-degree, even higher flow temperatures. The red line is where a proper gas central heat and condensing boiler would work most efficiently. So anything under that, so typically 55 degrees. And then the black line is where most of the heating systems in Europe are operating. So we're a long way off in Scotland in terms of overall heating design, next generation, low temperature heating. But so it's coming in, but very, very slowly. Against that background, we do have this graph on the right is solar irradiance in various parts of the world. And you can see the red is Birmingham. So it's not too far away from Scotland. And then the blue is Athens, which isn't too far away from the equator. Certainly a lot sunnier. So we do have a fair amount of solar energy here in Scotland. So I think that the thing is we're moving into an area where trying to do this peak lopping. So anything we can do to have storage, use whatever solar energy, free energy we can have, grab it, and then use it at different times is going to really help the transition to net zero and the network. So in a bit on the theory now. So this is how we would use, this is a solar thermal system schematic. So you've got a panel up here. In the old days, probably flat plate because they were cheaper to make. But these days, China's really come in board with manufacturing and managed to make evacuated tubes very, very cheap. And evacuated tubes, because you've got your heat collector in the middle of that tube, and then the vacuum is very thermally efficient. You've not got a loss of heat from the panel itself. So typically, most systems now would probably be evacuated tube. Inside the evacuated tube, you've got a very thin very thin capillary and you put it at a slight angle, and the water boils at the bottom, and it goes up and condenses at the top of the tube. You have the panel set at a slight angle, and then the liquid drops back down the tube. So and then that heat is in a sort of header along here, indirect header. So each tube supplies heat to a header, and then you would typically have a pumped pressurized circuit with evacuated tubes, or you have to have, really, because the temperature is so high, you need it at high pressure. So you'd have a pump station like this, sensor on the panel, and a sensor in your domestic hot water storage. And as long as the panel's hotter than the tank down here, the pump kicks in and it just circulates the fluid in an indirect method, we call it. So it goes through a coil and then back up to the roof. And then this system, because these are up on the roof and these pipes are outside the thermal envelope, you're looking at it having some kind of antifreeze in it, glycol mix, propylene glycol typically. So, and you also have an expansion vessel. You're going to need a safety valve as well. And the hot water cylinder here, you're trying to bring as much energy in as possible. So even if it's down at sort of 25, 30 degrees, you're bringing it into the bottom of the cylinder, trying to get the maximum benefit, and then the heat will rise up in the cylinder. It's not always sunny every day, and you probably want a shower every day. So you would have a backup system. You'd take in another coil at the top, and that's where you bring in your boiler. Or you might use electric immersion to top it up if you need it. Even if you didn't have backup boiler, you would have electric immersion to get it up to 60 degrees once a week for Legionnaires to kill off any bacteria. So there's a typical system setup. And then traditionally we've been using them for domestic hot water, although more and more we have been using second tanks or bigger tanks and diverter valves and things, and preheating boilers or directly feeding into space heating. But the temptation is to, well, the energy's free, solar energy's free, is to keep adding more panels. But the problem that we found with that is the more panels that you have and the less volume, you've got to dump the heat somewhere. So if you've got this system here, this simplified schematic on the bottom, and these guys modeled with 4 panels and a 200-litre cylinder, I think 300-litre cylinder. When you switch the system off, so they stop pumping, so say the temperature in the tank's got up to 60, 70 degrees, you don't want it any hotter than that, you stop the pump, the flow stops, so the heat isn't getting taken away, and you can see that the pressure here is rising up, so it went up from 2 bar, and within 30-40 minutes it's up towards 4 or 5 bar. At that point, at that pressure 5 bar, you might be generating steam. So you've got a very substantial increase in pressure in the system. And that goes back to expansion vessels need to be sized differently for solar thermals, or you'll have different mechanisms to the normal plumbing that your normal plumber's used to. And the temperature up here got to 152 degrees. So if you've got a glycol mix in here to help with freezing in winter, the glycol can break down at around about 130, 140 degrees. And you get this kind of gunky mess forming, and you've got narrow pipes, it blocks it up, the flow gets reduced. You can start seeing a lot of issues with solar thermal if you're tempted to oversize it. So I think that's the main issues with solar thermal. And because of that, not everyone's aware of it, or they're not dealing with it every day. The sort of installer base, they tend to maybe use too small pipe work. So, you know, the typical thing is you go up in a loft with an issue with solar thermal. Pipe work's really small. They haven't got the right fittings because you need special fittings to cope with temperatures up at over 100 degrees. So you can't, you know, in Scotland, you've probably got lead solder on pipes still. That's not going to work at that temperature. They've maybe got that grey Climaflex insulation that we see on pipe work. So, you know, they've ticked a requirement for insulation, but it's not rated to 130, 150 degrees, which you need the black EDPM stuff. So it's quite common. You go up, you'll see small pipe work, solder fittings, grey melted pipe work, grey melted insulation. The expansion vessel's probably gone because it's undersized and it's working too hard, or it's gone too over temperature. A lot of stress on the system, and potentially you get leaks in it, air admittance. If you get air in the system, you get a lack of flow as well, and then the whole thing gets worse and worse. So they're the kind of typical issues that we see. The controls as well. So sometimes we get solar thermal on social housing projects. It's a good idea because you're trying to reduce people's bills, but the execution of it might not be right. They might delegate it down to the trainees, and at the end of the day, or an electrician on site just to set it up and commission it. And they all want to go home, so they leave the gas boiler on running to keep the tank at 60 degrees all the time, which means that the solar panels never switch on because it will only enable if the tank's cold enough to bring the solar on. And then these systems can sit and stagnate all the time. So there's a few of the issues that we see. So I think the solutions to that are to use more storage, or to size it properly to meet your summer hot water demand. You might not use glycol. So if you've got really good engineer, or you can use some systems like the salt trophy, or maybe a drain back. But you're starting to use specialists now. They don't need glycol, so you can get around the problem that way maybe. And certainly you need volume. So I think this is just to finish up a couple of examples. There's quite a bit going on here, but there's a photograph in the middle of, this is all the same installation, but that's the pump station there. So they have got the correct pump station. They have got the fill and drain set up here. So quite often, sometimes I've just seen washing machine valves or something put on there because this is maybe 60 quid, whereas a pair of washing machine valves might be a tenner. So at least they put the proper one in here so that you can get the pressure up initially to quite high pressure. And you can see this is the pressure gauge on it. That's up at set at 4 bar, so it was probably set up there originally properly, but over time it's degraded and they've had air leaks and the pressure in the system's right down. If the pressure in the system drops down to half a bar or a bar and you're getting these high temperatures, you're more likely to get steam generating, and then you get a lot more issues, safety issues. You've got the blow off here. So if you get steam and the pressure goes really high, that blow off is going to open at 4 bar. You're going to drop pressure out the system. That's the other side of it here. So the blow off's going down. At least they're collecting the glycol into a little tank here. So you could probably see the system's losing pressure. Now you see they've got a radiator up here in the loft. So they've tapped in a radiator into the solar thermal, trying to manage the heat loss. So it was kind of working this system, and then they went away on holiday for 2 weeks, and it was the same thing. The cylinder just sat at high, get some sunny days in July. You're not emptying the energy out of the cylinder, and then the system just sat with the pump not running because it's not going to keep putting energy into a cylinder if the cylinder is up at 60-70 degrees. And then the pump just fills up with stagnated glycol and crystallizes, and you can see sort of gunk on around joins and things here. So that's kind of typical problems with solar thermal. But on the other hand, this is self-builder. So he's got a boiler here, and this is the solar thermal coming into a tank-in-tank system, where you can see there's 4 of these tanks. So they've got 3,500 liters of storage. And if you look at the kilowatts that are being stored in here thermally, that's a lot cheaper to do this if you've got the space than to maybe store it as lithium. So we're not saying solar thermal's always a headache, but it does need to be designed properly, and you might need to go to something pretty large with your storage to make this work. And then the heat network, the heating systems coming off here are all designed for sort of 35-degree flow temperatures, things like that. So actually the solar thermal can do a big chunk of the heating as well. So just finishing up, solar thermal, probably the poor sister in solar, but certainly lack of government support or proper government support. But I do think this peak shifting thing is going to become more important. You are offsetting thermal offset by means, you are offsetting probably a gas system or whatever you're using for heating, and that will be a genuine carbon reduction, even because the grid is decarbonizing. It's arguable how much more marginal benefit we get with solar PV offset. And if you can get better design systems, or you've got a building with summer space heat load like a large swimming pool, or you've got a lot of hot water, commercial building, hotels, still please look at solar thermal. And then I think just be aware of some of these drawbacks. It only does heat's fairly cheap, so the payback can be quite long, but as gas prices and heating goes up, I think we'll see that change. You do have glycol typically on systems, problems with disposal, this overheat. It needs to be managed and maintained so that the systems work properly. And because it's a poor sister, maybe not so many engineering, design and installers out there that are familiar, not many plumbers carrying solar pump stations and all the proper kit that you need. So, and I think it might make a revival, but it needs to be carefully managed. Just to finish, I think this is, if we were allowed to, in government policy was to let us do a lot more space heating. This is a large solar thermal array, large thermal storage, and it's in a district heating in in Denmark. So we might see systems like that in Scotland in the future. Thank you very much.
Thank you very much, Dan. That's very insightful. Brings back memories of what I installed 20 years ago myself and didn't size the expansion vessel right. Thankfully, that was a water system, so it wasn't glycol everywhere. Yeah, it's a really good pointers for detailed design for everyone to note. We'll keep all the questions in the chat if you can, but do keep them coming, and I'll sift them through, and we'll have Q&A at the very end. So and yeah, collect them all. So do keep asking questions in the chat. Just for the next couple of speakers, just now there was some issues on the sound. It mainly came over okay, but maybe the mic was too close to the mouth, and it's kind of a bit, you know, when you're certain sounds are a bit sort of poppy. I think that was what's said in the chat. So if Jez, if you could, and Steve, if you could look out for that, that would be great. So the next speaker is Jez Klimas. Sorry.
That's all right. That's all right.
He's been for many years principal engineer at Max Fordham. As all of you will have heard of Max Fordham's very top-end engineering firm, and have just joined Midsummer Energy as the head of renewable heat. So very much looking forward to your take on solar PV and all the installation, maintenance, and other design issues that might come up in that regard. Over to you, Jez.
All right, thank you, Chloe. Yeah, so I'm going to just share screen now. Can everybody see my screen? Okay, good. Yeah, so I work for Midsummer. So we're a wholesaler of renewable energy products, and Midsummer has for about a decade been a growing solar PV distributor and wholesaler. And I joined at the start of the year to start doing heat pumps and things as they've diversifying into a wider range of stuff. So I probably know less about solar than nearly everyone else at Midsummer, but still, hopefully this is useful. So kicking off, I'll just chat through solar PV installation and the parts of that, and then a bit about maintenance, and then application and integrated building energy design, because I think there's a lot of ways to get better value out of the PV and maximize the benefit that people are getting. So to start off, I'd start at the roof and work down. So the typical retrofit install is an on-roof install where, dependent on the roof type, you need different mounting systems, but quite frequently it's tiles of some sort. And I've got a photo of a tile hook here. Actually, I think it's a 3D model, but yeah, tile hook, and then you have a system of rails. And these are fairly kind of fungible things that one manufacturer makes a very similar set of stuff to another manufacturer. And sometimes you need specific ones for specific roof types. And you get into some very fruity ones when you get some, you know, standing seam and all sorts of other stuff. But most of them pretty much boil down to something that fixes to the roof, and then some rails, and then you put clamps on the rails that clamp the panels, and the panels have clamping zones where they're happy to be clamped. And that's how you fix them all up there. On new builds, it tends to be an in-roof system. The reason for that is to get it neater and to reduce the number of tiles you're having to buy. So you get a kind of win-win of a nicer looking roof and less tiles to buy. So this picture here is a very popular in-roof system called GSE, which is, it works the same way as Velux roof lights actually, and it actually integrates with them. So there's these plastic trays that go down, and then the PV panel clamps down and presses onto that to seal the roof and make it watertight. And that's very popular, and it works with a range of different panels. So on this one, those are optimizers, which I won't go into in too much detail right now, but yeah, you can see that's one fairly opened up. Then you also get some slightly better and neater in-roof systems. So this one here is a Solfit in-roof system. So with that, there's trims on the edges of the panels. So the panels are specially made for the in-roof system, such that the panels all slot together, and the waterproofing happens more naturally with less seals to be put in. And Solfit's actually it's a Scottish company, and they're just your typical Scottish engineering nerd guys who've thought about a way to do it better, and have come up with this lovely system. And it is very nice. Probably less concerns over longevity than using a number of seals that rely on material characteristics to work. So that's the roof. So then you've got to plug that together in DC cabling. So the PV panels produce direct current, not alternating current that you use in your house. So they all come with connectors, MC4 connectors they're called, and you have to plug them all together into a string, and that requires you to do some making off of the DC cables and crimping to connect into the MC4 connectors, and that's a major point of failure in PV installs. When they are wrong, it's nearly always that they've used cheap connectors or they've not made them off correctly. It's massively the one installation issue. I mean, a few things can go wrong on the roof, such as waterproofing and broken tiles and things like that, and damaged panels and panels not quite clamped down correctly. But more often than not, if something goes wrong, it's in the DC cabling and the connectors. So then, as you come down from the DC cabling, it needs to be converted to AC. So that happens via a device called an inverter. So that's it's just an electronic device, really, that cleverly takes the DC and turns it into AC at 230 volts, synchronized with your grid, and lets you use that electricity. Now, up until recently, these were nearly always string inverters. So this is a picture of a very popular string inverter we sell. So that simply converts the DC to AC, and if you use it in your house, brilliant. And if you don't, it gets exported. Increasingly, people are putting PV systems in with home batteries, and the most sensible way to do that is the battery is also a DC device. So it's to keep all of the battery charging on the DC side, with the PV directly charging the battery via DC, and then only converting to AC if you want to use the electricity, whether that's off the PV or the battery, and having a single inverter for the battery and the PV. So this on the right here is one of the neater packaged battery and hybrid inverter kits. So the top piece is an hybrid inverter and the bottom piece is the battery. And that's made by a company called Soltaro, but there's a bunch of companies making them. And they're getting increasingly popular because people want to maximize their self-use. Now, there's an interesting breakpoint at 16 amps of current, where if you're below 16 amps of current, which is 3.68 kVA or kilowatts, then, which is about a 10 panel installation typically, then you can just install it and the utility has to accept what you're doing. If you're going over 16 amps, then you have to apply, and that's these are guidance document references, G98. So people say a G98 installation, and that's one you can do without asking for permission. And then G99 installation is one where you have to apply to be allowed to put in a larger inverter, or a higher output inverter. So that's an interesting breakpoint, and it does mean that the most common PV install on a British home is about 4 kilowatts of panels, a 3.68 kVA inverter, and leave it at that, because that's a kind of good amount of power. That'll generate about 20 kilowatt hours on a sunny day, maybe 25 at the peak, which is a really good amount of energy, and it fits on most roofs, and it doesn't have a paperwork burden, or as big of a paperwork burden. So designing these systems, actually, there's a fairly kind of common standard through how it all works that means you can largely swap out one component for another at all the different levels. So we found that it was fairly easy to formulate that into consistent rules. So at Midsummer, we've got this design software, Easy PV, which you go to easypv.co.uk. It's free to use, with the idea that we sell solar panels and kits. So it's very easy to just draw the roof, populate it with panels, then go through selecting an inverter that works, and do a bunch of tasks that gets you through a full design, which all works fairly slickly. And then at the end, you get a bunch of installation documents. So here's one I did for my house. I haven't installed it, by the way. Don't get paid enough quite to afford this right now, but there's all the panels in a string, up in the DC part, a DC isolator going onto an inverter. So then it's AC from here down. as an AC isolator to isolate the inverter that side, PV generation meter, and then into the consumer unit, and then there's also the electrical meter there, and that's a fairly quick and basic schematic of a PV system for a house. So maintenance, it's a really interesting one, this, because essentially most people with PV don't do any maintenance unless something goes wrong. It's reactive, and that seems to be the most sensible way to do it for the most part. If your PV panels are subject to fouling in some way, then you might want to clean them. So, you know, some people get leaves blowing onto them, or seagulls are particularly keen on crapping on them. So that's always, there might be a bit of cleaning to do, and it might be prudent to do that even if they don't look dirty every few years. Once it's set up and working, the thing that's most likely to fail is the inverter, because they're pieces of electronic equipment produced to a cost, and some are more reliable than others. So in my rather enthusiastic design here, I did myself a Fronius Primo, which is a very nice Austrian inverter that are extremely reliable, but some are less reliable than others. And for the most part, they seem to get swapped out rather than fixed. You know, they're a few £100, and once they're out of warranty, people generally give up on them if they fail. But it's a fairly quick and easy job in that the cables are all there. It's not a long-winded job. Then essentially the way you know it's working is most inverters or other systems that you can get have monitoring. And so on the right here's some screen grabs from a Solar Edge monitoring system. So Solar Edge make very nice PV inverter systems, which also offer panel level optimization. But this lets you monitor what's going on, and most people I know who've got PV spend a bit of time looking at it, particularly on sunny days. They go, "Oh, I wonder what my PV's doing," and check it out, and bore their families silly. But it does mean that if something starts to go awry, they probably start to notice by looking at the monitoring, and that's normally the first sign, because there's not you know, aside from it completely not working, there's not normally any signs that anything's up. So I'm going to move on to integrating it into wider systems then. So self-use is the kind of key concern. People have spent money on a PV system or spent money installing it on a new home or whatever, and they're then concerned that they get to use the electricity they're generating. And whereas with solar thermal, the storage is inherent and you can't use it without having a store, with PV that's not really the case. So it's fairly typically the case that for a house without a heat pump for the moment, with a string inverter, people typically use about 30% of what they generate. So they get a bit in the morning and a bit in the evening, and their house has a bit of base load while they're out of keeping things ticking over. And they typically use about 30%. Obviously, it varies a lot. If people are working from home, they'll have a greater amount of self-use, and if they're doing electricity-intensive tasks in the middle of the day, kind of deliberately, you know, scheduling their washing machines to run in the middle of the day and things like that, then that can help increase it. But then battery systems are getting increasingly popular, and that jumps you from around 30 to around 70% self-consumption, possibly even higher. And for that reason, they're getting increasingly popular. Now, last time I kind of did the calcs for myself, it didn't change the payback period really of doing the installation, because although you get a lot more electricity out of your PV array that you can use yourself, you pay more for the kit to do it. But I just think people like the idea that having generated the electricity, they don't want to see it go straight out the door. So then, if people did have a heat pump, which increasingly they're going to, then that will increase self-consumption. Now, there's a lot of factors at play in figuring that out, to do with the relative size of the PV array and the heating system, and to do with how they operate it, and when they schedule hot water runs and things like that. So even finger in the air estimates are a bit tricky with this, but I'm looking at the moment at some new build housing, which is, you know, good, efficient new build housing, that they're putting 4 kilowatts of PV on the roof and they're having 4 kilowatt heat pumps on each one. So that's got 1.5 kilowatts of peak electrical use. And that does mean that for fairly decent chunks of the year, there's some support of the heat pump running from the PV, and it's particularly helpful if you've got a battery that, you know, the sun goes in and out sometimes, particularly, you know, in spring and autumn. You can have those lovely sunny crisp days, but it might be the clouds are scudding over, so the battery kind of smooths out that consumption and lets the heat pump use it some more. So what there isn't is a direct linkage. You'd be amazed at how many times people have said to me, can't I just run the heat pump off the PV? And no, you can't. It's aside from anything else, that would mean you only had heating when it was sunny, and that the heat pump would have to run at a speed that suited the amount of solar generation, which wouldn't be very helpful. So there's no direct linkage there. The heat pump uses alternating current electricity, and the inverter and battery produces alternating current.
Too much space.
Oh, we've got somebody's come on the chat.
Space there.
Can we could we mute Pauline potentially? Oh, there we go. Right. Yeah, so there is some synergy, but it's not a super strong synergy, because it's generally, if it's going to be very sunny, then your heat pump isn't going to be doing very much work. So the kind of support of the amount that the PV supports the heat pump is only really significant on very low heat loss houses with quite a lot of solar. But actually, on a lot of new builds, that can be the case quite easily, and on a, you know, really good deep retrofit also can be. So then the next level of kind of maximizing your self-use is using PV diverters. So what a PV diverter is, here's a picture of one. That's a My Energy Eddy, which is one of the more popular ones. So it kind of monitors your meter tails and looks for export that would be occurring, and then it skims off all of that potentially exported electricity, and it can put it into the immersion heaters of hot water cylinders. So this is a direct electric hot water cylinder with 2 immersions, one near the top and one near the bottom. And so this is kind of the electric solar thermal. And what's nice about it is that, so say your house was going to be exporting 400 watts, it just skims off just that much, so that at your meter there's no import, no export, and the excess PV generation is going into your hot water, and it responds quite quickly to track the amount of excess PV generation. And it doesn't suffer the same kind of overloading and heat dumping type issues that solar thermal has, because so a fairly conventional way to operate this cylinder would be that the eddy would charge this top immersion, and then when that immersion hits its set temperature, say 65 degrees, it turns off, and then the eddy will charge this one and charge up the rest of the tank. And once that one hits 65 degrees and the whole tank is at 65 degrees, it stops putting electricity into it and starts exporting the electricity, and you get paid for that instead. So this is getting kind of increasingly popular because it's all solid state technology that doesn't require a lot of maintenance. So it's a lot less faff, but ultimately it's using fairly valuable energy for a kind of lower value use, and use a lot more roof to do it than if you're doing solar thermal, which is its downsides relative to solar thermal. Now, another thing you can do with these is you can get a relay board for an inverter, for a diverter, such that you can trigger the heat pump into hot water mode, or indeed slightly increase the temperature set point when you've got sufficient solar generation. So a fairly common way to set it up on a new house might be, you say if it's less than 1.5 kilowatts of excess generation, then it'll put it into the cylinder via an immersion, and then once it gets over 1.5 kilowatts, enough to run the heat pump in a hot water cycle, it triggers the heat pump into a PV driven hot water cycle. So that's a really nice way to maximize the self-use and kind of not waste it, because it's nice if you can do it through a heat pump rather than immersion, because in immersion you get 1 unit of heat per unit of electricity in, whereas through the heat pump you get 2 or 3 units of heat per unit of electricity put in. So we've kind of tried to build this in, and it's an area that we've worked on and the products we've been bringing in. So we do pre-plumbed cylinders which simplify the install of a heat pump, and we've got twin immersions on them. So one immersion the heat pump controller has to be in charge of to do Legionella cycles, and the other one is available then for PV divert. But then we've also got some other products that have really caught my eye before I started selling stuff, and both of them were happy for us to sell them, which is mixed use cylinders and sun amps. And both of these have a real advantage as electric water heaters, that as soon as you start putting electricity in, they start generating hot water at the high temperatures of, proper hot water. So the mixed use got an immersion right at the top, so it heats the very top bit of the tank first, and then this little pump pumps cold water from the bottom up to the top, and that hot layer just gradually moves down the tank. And so when it's 50% full, instead of the whole tank being at 40 degrees, the top part is at 60 and the bottom part is at 10. And it's that's nice. And the sun amps are another piece of Scottish technology, and they're phase change heat stores. So they're much more compact than a hot water cylinder. They can store 4 times as much heat in the same volume, and so they're really good for keeping space down and being able to store a lot of energy. And it melts a phase change material block inside here, and there's a heat exchanger to extract the heat from that. So cold water goes in, hot water comes out, and it basically acts like a hot water cylinder but in a much smaller space, and they can be PV charged. So they're both really good, and they both can be heat pump compatible as well. So it just lets you have a kind of integrated energy system in your house that lets you really maximize the amount of your PV use you're taking and how low carbon your heating can be as a result. So yeah, with the Mixergy, this is Mixergy's graph, so you can schedule how much of the tank you want hot at a given time. So you schedule it to be hot before your showers, and then to be only 20% full following your showers, and that leaves all this free capacity to be charged up by surplus solar energy. So yeah, people have seemed to be very satisfied with the results on that. But then you've got to kind of think of what to do with this energy that's potentially being generated at a time where you're not able to use it. And a kind of fairly typical self-use hierarchy that people program into the systems in their houses, first of all, charge up the home battery so you can use that energy later when the sun isn't shining. Then an EV charger if you've got an EV that's plugged in at the time. Then into hot water, and then you can also program a lot of heat pumps to bump the temperature set point of the house up by 1 degree, so you can slightly overheat the house with excess electricity. And then last of all, export it so that you're helping decarbonize the grid outside of your own home. Okay, and that's me done.
That's great. I think it almost just about covered some of the questions coming up as well in the chat. So last but not least, we've got Steve Dubb coming to talk about the Bullet Center. Steve is the Senior Associate at Miller Hull Partnerships, Project Architect and Construction Administrator for the Bullet Center, designed under the International Living Building Challenge and City of Seattle Living Building Pilot Program in waiting for this moment for a long time, for some of us at least.
Great, thanks, Glo. It's really a privilege to be able to present the project to everybody today. The Bullet Center is a very important project for our firm and our practice. It's in one way, it's a culmination of a lot of research and design effort that and an ethos that's been part of the office since its founding. But it's also been a project that we've been able to sort of do everything all in one place, and the things that we've learned from this, we've been able to apply to other projects, other living buildings. So we love to talk about it, and so hopefully this is a lot of these lessons learned and techniques and strategies will help folks here that are trying to implement change on the project level. I know the last 2 weeks it's been a very high level and important conversations at the COP summit, but hopefully this will be a value for people moving forward. So let me see. I didn't get my advance here. There we go. Is that advancing? No. There we go. So the Bullet Center opened in 2013. We started design in about 2010. So about a 3-year design and construction cycle. It's net zero energy, which we'll mainly be talking about today. Net zero water. So all of the water supply for the building is collected by the roof and stored in a cistern, and that provides all of the water for the operation of the building. We've also eliminated, as part of the living building requirements, over 360 different hazardous chemicals that are typically found in many building products. That's posed a lot of challenges during construction, because often only 1 or 2 options will maybe be available for a certain material, and then an additional cost might be associated with that. But we were able to, products that we've identified from here, we've been able to use in other projects. So I just wanted to also quickly talk about Dennis Hayes, who's sort of the face of our client, the Bullet Foundation. Some of you may know Dennis. He was he founded the first Earth Day in 1970, and then he was also the head of the Solar Energy Research Institute, which is now NREL under the Carter administration. And so I can't stress how important it is to have a client that is so committed to the goals of the project. There's, like in many projects, there were so many times that these goals could have been compromised, especially in regard to net zero energy and the materials red list. And it was really Dennis's commitment to that allowed those values to remain intact. The building was built under the Living Building Challenge. This was a constraint of the design that Dennis brought to us as the firm. If you're not familiar with it, it uses this metaphor of a flower with 7 petals, and you have to sort of meet the requirements of each petal to be considered a complete living building. So there's issues of site. You can't build on green fields, as an example. Net zero water, net zero energy, health, having to do with mainly daylight and ventilation, the materials component. There's an equity component, and then beauty, which is a very kind of squishy topic. But the main technical challenges were around net zero energy and net zero water, and then obviously the material selection. The great thing and the bad thing about the Living Building Challenge is that it's not a prescriptive rubric. So you just have to be net zero energy. There's no points or other ways that you, requirements you need to meet. How you get there is really up to you. So, there's simple rules with, sometimes complex solutions, and they're not necessarily complex in a technical sense, but they're complex in that there's a interrelation of all of the different parts of the solution. And so changing one thing will affect performance of another. So let me see here. Sorry. So what we'll do here today is we're going to talk about the net zero energy portion of the project. You know, any one of these topics could really be a whole discussion in itself. We're going to talk about the availability or capacity of the site for solar generation, and then talk about gap analysis between comparing a existing typical building in Seattle. And then, you know, how do we step down and meet the energy budget that's basically established by the solar capacity. So Seattle's up here in the upper left, and it's probably the worst place in the United States to try to do a net zero building, or at least the most difficult. There's certainly better places in the Southwest that have a lot more solar potential. We have about 1,200 kilowatts per square meter per year. I think looking up on the internet, Glasgow looks like it's got about 1,000 kilowatts per meter per square meter per year. And Dennis's point to us was that, you know, if we can do a net zero building in Seattle, you can really do one anywhere in the United States in terms of net zero energy. Net zero water, maybe a different discussion, especially down in the Southwest. The site was given to us. The Bullets Foundation had already purchased the property. It's on Capitol Hill. It's at the top. There's a park that's owned by the city. So it has great solar access. The zoning around it is such that we've basically got, you know, guaranteed long-term solar access. But downside of this is it's an urban site. The building goes lot line to lot line, so there's not really a lot of extra room to put PV. So the real exercise to begin with was to decide how do we maximize the amount of panels on the roof, or on the building rather. So we used a Rhino model with a program called Grasshopper, which allowed us to, you know, rapidly look at different configurations and, you know, parametrically change the configurations of the panels. And then it would tell us, you know, is this configuration better or worse? We did a lot of studies. This is just a few of them. Ultimately, what we found was that quantity really governs over any optimization of panel orientation. So if you can imagine trying to align panels to some, you know, attitude towards the sun, then they begin to shade other rows. And so it's actually more efficient to have everything flat. So you can maximize the number of panels was sort of the main rule. But that put us in kind of a weird place. So this is actually the panel configuration that we had for a very long time into probably halfway through construction documents. And what this is really maximizing the amount that we could put on a horizontal surface. We're using the allowable zoning variances for projections over the property line here. And then we're using a transparent sort of bifacial panel on this south facade to kind of get us to the budget that we thought we were going to need to even with aggressive energy saving measures. This is the amount of energy that we would need to make net zero. Fortunately, technology sort of caught up with us, you know, went more quickly than the design process. And we went from a panel that originally was about 315 watts per panel to these panels, which are about 425 watts per panel. So we were able to completely eliminate that south array, and it did a lot of things for us. It improved daylighting into the building. It reduced a lot of structure that was kind of causing us some budget issues. And with this configuration, the new panels, we were able to get about 242,000 kilowatts per year projected. So that's sort of how we got to the form that you see in the built project. We were able to take some of the money from the structure that we had saved by eliminating the south array and actually cantilever the roof array. So we got rid of a lot of extra columns that you saw maybe in the previous rendering. And then so that really established our energy budget. And then you can see here on the left, typical baseline office building. These numbers at the bottom is a EUI, which is an energy utilization intensity. And I think the measurement is in, the units are in kilobtus per square foot per year. And so a typical Seattle office building gets 90, 92 as an EUI. The capacity of the solar panels was really equal to about a 16. EUI says about an 83% reduction that we were needing to make over a baseline building that was being built at the time. And so the ways that we did that really fell into 3 different categories, sort of reductions of loads and increased efficiency is in heating and cooling, and in lighting, and then in tenant or occupant behavior. And based on our studies and working with our engineers, we felt like implementing all of those measures was going to get us down to this net zero energy use. So I'd like to go through sort of each one of those categories, and we can kind of talk about the efficiencies that we made to the systems and ways that we were able to reduce the loads on the building. So under heating and cooling, so the first thing that we try to do is, get the best envelope that we can really afford. So opaque walls and glazing. Seattle has a fairly aggressive energy code. At the time, you can see the numbers there in 2010. Actually, the Seattle code now is basically equal to what we have for the bullet foundation column there now. So a roof in Seattle has a required R38 R value for its insulation. Glazing, to get to R4, which is about a U value of 0.25, we used triple glazing. And then a new thing in the Seattle code was air infiltration. And, this has become a big topic for under sort of the banner of energy efficiency. We've been discussing air infiltration or air leakage in the context of water and moisture mitigation. There were a lot of condominium failures in the 80s. And so there's a lot of consultants out of Vancouver, British Columbia, that had to deal with this. And one of these things, one of the issues that they were finding was that the air leak was just causing a tremendous amount of condensation within the wall assemblies. So we had better and lesser success getting contractors to do tight air barriers, but now that it's been part of the energy code and the city has really embraced it and codified it, we're getting much better numbers. So you can see we've got a 0.24 cubic feet CFM per square foot for air leakage, which is fairly tight envelope. In terms of the mechanical systems, Dan and Jez, it's really a lot of the same things that we've already heard about today. This is a ground source system using heat pumps. There's 26 400-foot deep loops. They use a glycol mixture, and those serve for hot water and radiant heating in each floor. So each floor has a radiant slab for heating. We've got on-demand ventilation. So that's either done through a mechanical system when it's either too hot or too cold to use outside air. We also use natural ventilation through operable windows. Any air that's exchanged to the outside runs through a heat recovery unit, and then it gets put back in to the system. So another way that we're reducing loads on the building is we've got exterior shades. That does a lot to knock down the heat gain during the day. They're tied into the building management system. So as the sun comes around, different facades are controlled, and these blinds deploy. They lower and they can tilt. They when the sun comes around and they're not needed, they retract back up into that housing. You can see the windows are also operable. They're also tied into the BMS system, and this does a couple of things besides natural ventilation. In the summer, we can open these up in the early morning, and that will pre-cool the slabs of the building to kind of cool the inside, and it does a lot to reduce cooling requirements during the day. So on the lighting side, the game here is daylighting. We can do a lot with, or not a lot, but we can do a bit with reducing the amount of power distribution per floor. So not having as high as watts per square foot for lighting, reducing that, using daylight dimming. So if we're using, it's having sensors on the lights. So when there's sufficient daylight, the lights will stay off. We used a program called Ecotect to do most of these studies, and we did a lot of studies. You can see we typically, as you would expect, had better illumination around the perimeter. So that's where we've zoned office space. More of the core elements like elevator and bathrooms are in this sort of middle portion. We also learned from these studies that this is a photo of the interior, that having windows that went from floor to ceiling and were evenly spaced got us better and more even illumination. So even in detailing the perimeter beams, we upturned it so that we could get the window all the way up to the top and get the extra reflected light from the ceiling and the floor back into the space. So the trickiest part, the typical floors were pretty easy. The trickiest part was we had this solar array on top of the building, and that shaded the entire 6th floor. And so you can see this is the Ecotect sort of lux output. It's you can see lux on the side there. So there's a cutoff at about 269 lux is kind of our lower end, up to 1,000. And the way we solved this was sort of clever. We had the issue is that we have a structural bay that's one size, and we have a PV bay that's much narrow. So what we did is we basically indexed a sort of light well with the skylight size to the PV panel array, and then a splayed opening that was indexed to the building grid. And we got a much better distribution, and I think actually in a way more even than a typical floor. And here's an example of that photo, so you can really see how the walls of that sort of splayed opening can really catch the light. And this is, you can see there's really no overhead lighting here. So for the most part, even on a gray day, they don't use the lighting really that much. So On the tenant side, the first thing we really needed to do was to challenge conventions around comfort. I think a lot of people think about air temperature as sort of the main index, but there's really a lot of other things that you can affect to kind of change your perception of thermal comfort. For instance, airspeed, we use fans, ceiling fans that allow the air to move around, and just that sort of convective cooling of the air circulating does a lot to affect your thermal comfort. The radiant heating and having that conduction heat to your feet also gives you a better sense of thermal comfort, which is a lot more effective than sort of convective heating. We do have some amount of individual control for ventilation. We found that having an occupant having perceived control of their environment, they also feel a lot more comfortable, just because they know if something they want to change it, they can. They don't always do it. In fact, most times they don't. But just the idea that they know that they can change it affects them sort of psychologically. Another kind of feature that's sort of user-based is their lease. We have this sort of green lease. So each tenant has an energy budget that fits within that energy budget for the whole building. So at the end of the year, everything needs to zero out. And if you as a tenant happen to be over your budget, at the end of the year, you get penalized and you have to pay back the difference in the energy use. This is a picture of the dashboard that's in the lobby, and there's one on each floor. And so you can in real time get a sense of your energy use. So there's a lot of metering in the building, because one of the main interests for dentists was to get the data of use, but it also allowed them to monitor for this tenant this tenant requirement for staying within the energy budget. We also felt that, like, being able to see the energy uses of other folks, tenants between floors, gave a little bit of a sense of competition. And so I think everybody was very aware of being in a living building and how much energy they were using, and they were always referencing this to make sure that they were sort of staying within the bounds of their budget. So other tenant use measures that we implemented as part of the lease, daytime office cleaning. So no cleaning is done at night, because the additional energy used in illuminating the building to do cleaning would have blown our budget out of the water. We eliminated phantom plug loads by having occupancy sensors at each workstation. So if you left for the day, your charger would power off. Your whole power strip at your desk would power off. So really at night, the only things that are really running are the building management system, the refrigerators for the kitchens, and any systems running off the BMS. One of the sort of, besides the PV array, one of the more prominent design features is what Dennis called the irresistible stare. And we found in our calculations for the loading that for the energy loads, that the elevator was going to be 3% of the energy budget. And so we can't do a lot to design around what the user is going to do. But what we did is we moved the elevator out of the lobby and further into the building. And so really, when you come in, the only apparent way to get up is the stair. And it's all glazed. You get a beautiful view of downtown. And what we found is that the University of Washington did a study that about 2/3 of the trips up to the 6th floor of the building were used by the stair, done by stair. And so that actually ended up working, being an effective design strategy that affected, user behavior. We'll talk a little bit about a lot of the modeling that we did, and then how did this really end up performing? And just to give you an idea of what portions of the sort of energy budget went to what is represented in this graph. So you can see about 23% is lighting. There's a pretty decent chunk for running the mechanical system, space heating and cooling, the ceiling fans, the on-demand ventilation, all the pumps for the mechanical system, and then the sort of miscellaneous equipment chunk. And so what we ended up finding was sort of to the right is that modeled sort of pie chart that we were just looking at, and then on the left is the actual use. And so we ended up sort of over designing the PV array by about 25%. And I think there's several reasons for that. One is equipment got more efficient over time, and so loads that we were planning on for computers and office equipment, those things have their energy use is greatly reduced in the sort of 10 or so years that since we started designing and planning these buildings. We also I think made some assumptions about the tenants that didn't quite bear out. I think we originally looked at ourselves as an organization, as an architecture firm, and what would that look like if the building was full of engineers and architects, because that was sort of the tenant profile that the Bullitt Foundation was looking for. So, everybody had to have 2 monitors and a computer and a laser cutter and all of this equipment. And the reality of it is that we had one engineering firm, and then we had a lot of firms that really just had a bunch of people with laptops. And so so the energy use from computing went way down. You can also see that lighting decreased quite a bit. And I think that had really to do with the effectiveness of the daylighting. And I think once people got used to the lower levels of daylight, they just didn't turn the lights on. You can be here in an overcast day, and I think we have a daylighting factor of like 2% on an overcast day. And it's really a pleasant space, nice soft light in the winter. And it's like half the amount of energy for lighting that we were anticipating. HVAC is less. I think one thing that we did with HVAC is, because of this comfort modeling, we were able to justify changing the set points for the system. So everything runs a little bit, nothing kicks on, it's a lower temperature for the system to kick on and a higher temperature for, the cooling to kick in. And so expanding that sort of comfort zone also helped in reducing that HVAC number. And I think people just are used to, not always being at, 70 degrees and 50% humidity. So a lot of this has to do with changing, occupant expectations in their environment. One thing I'd point out, because the previous speakers have talked about storage, is in Seattle, when you've got a solar system, it's basically net metered. So everything that your solar panels are generating goes back into the grid, and then you pull back from the city grid to run your building. And because of the size of the array at the bullet center, it basically qualifies as a private utility. And as such, they were able to negotiate their own rates to sell back to the city. And so this surplus of energy and it actually ended up being kind of a financial windfall for the foundation, because they had negotiated such good rates and we had overproduced. All that money came back to the foundation. So you know, you can look at that we maybe over designed the building, and we could have, I guess, had less efficient equipment, or we could have
I think you become muted, Steve.
Yes, I can't hear either. Something's happened. Steve, can you hear us? Is everybody else also have a voice cut?
I can hear you.
Steve, can you hear us? Apologies, there's some technical issue. No, we can't hear you yet.
Oh, really?
Ah, yes,
Oh,
you lost.
yes, you're back now.
Oh, I'm sorry. How long was my audio off? I'm sorry.
2 seconds, right at the very end.
Just
Oh,
yeah.
okay. Gosh.
So maybe just go back a couple of slides or something. We got to the point where we did the modeling and the actual. As you change slides next, that's when
So
it
you
stopped.
told us how you got a windfall. That was about the last. you said before.
Okay. Let me see if I can pull that up.
Because you'd negotiated such a good rate with the city.
Right. Let me see if I can. Why am I not? Huh, it's not launching again here. Oh. Let's see what I did here. Oh, there we go. Let me go to the end. Well, I guess it was really just a follow up on, you know, some folks see this as, you know, did we over design the PV array? You know, I guess we could have used less efficient equipment, had a less efficient envelope. We could have reduced the PV array, but you know that with this rate, it really didn't matter because they were still getting the benefit of the overproduction. So this, you know, it was not it's not like, I felt like it was not always a sort of like, you know, we over designed it as much of it would just everybody did better than anticipated in the use of the building. The amount of energy produced by the array is almost exactly what we had predicted. It was really the variability and and I think on the occupant and tenant side, and you know, they're changing their behavior to not really, say for instance, need as much lighting all the time, and so they even use less than we had anticipated them using. And then my last slide here is really just to talk about the importance of having a dedicated team of experts and contractors, and including city agencies that really share the values of the project and what you're trying to do. And just like having a dedicated client like Dennis was really critical for us to be successful on this. You know, we really couldn't have done you know, had the level of performance that we have if it hadn't been for all of these folks here on the design team.
Thank you so much, Steve. That
Thank
was
you.
amazing journey. One of the quick things that we could probably answer is how long did the whole overall design take? Because obviously, clearly technology and all sorts of things changed through the design journey. How long was the process?
You know, it went a little bit in fits and starts. We had a big, because it was part of a city process. Also, there was a pilot program that the city of Seattle also instituted. So we had a technical advisory group that we met with. So it was a bit of a public process. I think design was about 2 years, and I think construction was about a year, 18 months, something like that.
That's great. I didn't know this beforehand, but Jez had to disappear off, and I see that on the chat that there are some quick answers to some of the questions. So from that, I think that what is quite clear is we clearly need yet another session to go on different configurations and combinations, probably with solar thermal and PV systems put together, and how things tie up controls, different diversion models, different inverter size, whether you use G98 or 99 for sizing of outputs and things like that. But hopefully those who've asked questions of Jez actually got at least some level of answers out of that. And I hope that Dan, you might be able to infill any other questions coming out up on that front. So if we roll back a little bit to some of the questions that came up, Dan, how do you see Scotland's grids faring in terms of using air source heat pumps that due to the embodied carbon of the UK versus Scotland? Should Scotland's be less than 100 grams CO2 per kilowatt hour?
Yeah, Scotland's already well under. I think they're talking about revising next year to 200 across the UK, but Scotland's all round about the 100, if not under. And there's times we're close to zero. 2030, Scotland will be pretty close to decarbonised on the grid.
That's great.
Obviously the network's balanced across the UK, so it depends on your view, but that's what I mean. It's less and less about saving carbon with PV, but the cost of, you're trying to match it to your own usage in a domestic building or a commercial building. You're trying to match it to exactly the amount that you're, like Steve showed in his modeling. The most cost effective is to get that sweet spot of the capital cost of the array and then the savings of having to buy in grid electricity, and that's just going to get more and more expensive.
Yes, the interesting thing is Living Building Challenge aims for regenerative and architecture rather than just sustainable, and I think that's actually really needed in the developed world, where places like Bangladesh can't actually meet their base load for energy because of densely population, and as well as no land to put up their PVs and wind and all that. So globally we have to make up for it. So I guess we should all aim for negative rather than just zero. So that's interesting though, when if you just talk about Scotland's already different from UK. However, moving on, there's a chat about sort of underfloor heating, whether it's preheated or whether we use solar thermal for doing underfloor heating, Dan?
Yeah, I mean, not many houses have underfloor heating, but if it was new build, or you can design a system with a low flow temperature, underfloor heating can work pretty well most of the year at 30 degrees. It might go up to 40 in the winter, 45, and when it's below freezing, but that's absolutely perfect. So I think that's the point I was making. A lot of solar thermal for heating's been neglected or not been looked at over the years because we run our heating systems at 70 degrees or 60 degrees. So having something coming in at 25, 30 degrees doesn't make much impact on a radiator. But yeah, we need to be more European and have low temperature, more futuristic in our overall heating design. And then at that point, solar thermal can make a really good contribution. You can have probably more collectors on the roof so that you don't have this overheat problem, stagnation, because it can divert and drop it into your underfloor even in the summer if it needs to.
Yeah, that's a good point, because we oversize our boilers and such and have peak loads and rather than a general load properly designed. It's a big problem in this country, waste a lot of energy. But we also have another question about, that's something that Jez was on about, PV diverters. Don't know if you can cover about that. Dan, use of PV diverters for different things, for cars, for off-peak loads controls for that and all that.
Yeah, I think if it's a straight choice, you would probably go solar PV and use diverters, because power is always more valuable than heat in a way, and you can produce heat. You can put it in, drop it into your hot water tank, or you can charge your EV car. You're always going to have a load. You're always going to have a use for it. And cost of buying in grid electricity is high, so cost of diverters are a few £100. So it does make a lot of sense. I think we have to be aware, though, that as we decarbonize, heating's going to be more and more of a problem, and you get much more solar input from solar thermal in the heating season. So you've already got a higher efficiency, but you're also collecting. You don't need direct sunlight for solar thermal. You can still get 30% of the indirect energy can be harvested using solar thermal systems rather than solar PV, or you've got limited roof space. So I think that probably the solution is both technologies need to be taken forward, and we might see more and more people coming around to having both, or having a mix with PV thermal.
Yeah, that's good. I think that's what we will definitely go on to, looking at intelligent systems. I think that word intelligent building actually came out a couple of times in the chat as well. How we can combine technologies, combine active and passive systems intelligently to make the best energy consumption and all of that out of it. Interestingly, the Kerr McGregor Award that we're going to announce later after Q&A, few years back, we awarded to the person did the AI behind the SunAmp latent heat collection, which is what Jess actually talked about as part of the intelligent systems, and works really well. And yeah, so we will definitely go on to that. And also, maybe not too many spoiler alerts for later on, but the future list of things we're going to talk about in next year's program. Let's move on to intelligent buildings. Steve, we're looking at your building with great admiration. We wondered if you know how much the occupants actually contribute or impact on the overall energy consumption. Is that something you know?
Well, impact in what regard?
So how the energy consumption, so like how the tenant behavior and giving them control systems, do you know how it compares with, say, a non-building that's not as intelligent, maybe?
Well,
monitoring.
It's hard to tell from the baseline, because I don't know that we've had very many good studies about the baseline. I just know that it's less, probably by about 25% than of what we had anticipated, and that had a lot to do with we came up with that baseline by basically surveying our office and actually the offices of all of the people on the design team, so the mechanical engineer, the contractor, and just to kind of get a range of like on the water side, like who rides their bike or goes for a run in the over lunch and needs to use the shower, and so that kind of helped us determine the carrying capacity of the cistern. So it's a difficult. I don't have great data to be able to tell you that, but it did
that's
have
at
a
least
lot more
some.
impact than we anticipated.
Yeah, how many people actually work in the Bullet Center? How many people does it serve? Do you know?
That also varies quite a bit. So PAE, who's our engineer, they have one floor on the building. They have probably about 30 or 40 people. The Bullet Foundation, who has half of the floor, only had 12 people. So the density of the layout varied quite a bit with the actual tenants and the design tenancy. When we did our sort of planning diagrams for the floor plate, we had those maxed out, and so we that was another reason why I think the energy use was so much lower, is because the density of occupants was much less than we had planned.
A question from Rich says, now that we have such low cost grid scale renewable power, how critical do you think the on-site net zero on-site generation is to sustainable design?
Is that a question to me?
Yeah.
Yeah. I think, we've done this sort of thought experiment. The world can't be full of a bunch of bullet centers, and really where we feel like things really need to go are to sort of these regional solutions for power and our neighborhood. So there's several organizations in Seattle that are trying to kind of get people organized. Sometimes you just don't have the roof area and you can't get the efficiency down to make that leap. On every project now, we do one of those gap studies. So compared to the baseline and how much PV potential you have, what do you need to get there? It's really based on what the design is. What PV would you need to get to net zero? And sometimes that's doable, sometimes it's not, and a lot of it has to just do with site and access.
Yeah, like going back to sort of Bangladesh's issue, isn't it? If you've got land and if you've got space to do it, then
right.
All is possible. There is a question, I think it's a general question for anybody who can remember. Actually, I think it possibly was answered in one of our earlier sessions about embodied energy of PV panels versus the lifetime energy produced, back when we had our LCA embodied energy session, but I'm not very good at remember answers. I don't know if Colin or somebody else has been there, whether they remember, or does Dan know the answer to embodied energy of PV panels versus energy produced?
I think we had the seminar on it. It depends whether you can always assess this peak thing where the grid is at high carbon and you're offsetting that in the middle of the day. So, but on general, I think it was a few years on PV. It's difficult to say if, again, as the grid's decarbonizing and what you're actually offsetting.
I think it's talking about embodied energy as well. Yes, it's time that we all look back, obviously, because I certainly don't contain numbers in my head very well.
I would need to look back and notes, Glow.
Yes, we do, don't we? Or the magazine article.
Oh yes, or the magazine article.
So yes, teach me something and I forget. But yeah, that's actually very interesting. So the next very, very exciting thing is to reveal the winner of the Kerr McGregor Award for Solar Innovation. Let me share my screen. You can find it. We had a very interesting shortlist of contenders. Sterling submitted a solar collector oven, a cooker, sorry to say, that allows collection of sunlight. into concentrated evacuated tubes, concentrated into evacuated tubes to be able to cook in a large oven and cooker for Africa, or currently deploying in Africa, should we say, which is very practical and serves many people, intended for hospitals, schools, or large organizations. So a very implementable thing that's going out there, being prototyped and tried out. We had Ellie Tanaka, who submitted a indoor low light energy collector for things of internet. I think the gadgetry, I suppose, indoors, so that it's easy to make. It's got titanium dioxide paste with electrolyte solution, iodide solution, that's dried on. So previously these printed electrolytes are liquid and very difficult to manufacture and leaks and all that sort of stuff. But by drying it, actually it's proven that it still works under low light and can charge all the gadgetries indoors. And we had another submission on solar kiln drying timbers that is working off PV fans and absorbing solar thermal energy and works by just heating and cooling through a diurnal cycle of normal days. So as sun rises, as heat goes up and cools overnight, and air is drawn through the container, as you see there, by solar PV driven fans. The judges were myself, Puiwa, and Colin Porteous, and we had such a tough decision between the three, looking at the impact of potential impact of each of the submissions, and also obviously innovation points, I suppose. And the winner is Ellie Tanaka, a new type of solid state dye sensitized solar cell based on polyiodides. We felt that innovation is a major step in development for it to be easy to make. It's simple, very low maintenance, hardly anything to go wrong with it. An application to low light effective photovoltaics, which is very applicable to drive down the energy demand from grid if we're going to charge everything indoors, all our gadgets that needs charging. The impact is that is possible to manufacture locally all around the world inexpensively. So instead of buying PVs from China, you could be doing local production of these things as a future trajectory. So it could be disseminated, and yeah, and also because there's no plastic encapsulation in this method, there's a potential. They haven't actually researched it just yet, but there's a potential of better or easier recycling options at the end of life. So we feel that that's innovative as well as yeah, impactful. I don't know if Colin or Puiwa wants to add any words to that.
No, I think you've covered that well. It wasn't an easy decision. Maybe the only thing to add is that although there were just these three submissions, that the range from a kind of very low tech end to quite high tech development end on the PV was the oven kind of somewhere in the middle, but because some of the technology was new and some was existing, or it was a new way of putting existing technology together. So it was a really very hard decision to come to, but so they were all very worthy submissions.
Yes, and hence we actually wanted to show all of them, and yeah, share it with everyone. These shortlisted projects, good. So next coming up is the show and tell, 3rd of December in Space Architecture Center. It's an in-person event with SEDA. And yeah, lots of people are going to present their 5 slides of what's been happening during COVID, maybe, as well as all the interesting things that's happening over COP, potentially. And for next year coming up, the solar series, at least, we're going to have a lot more discussion about what is available locally, what we can buy, make, and use here, both in UK and also in Scotland. And yeah, so what kind of other things are out there we can do. And I think we'll also touch on the various other integrating solar systems, as we talked about earlier, how we put the solar thermal and electrical bits together intelligently. I think that's all from me. Thank you very much for both attending, speakers for speaking. Thank you, Dan, and thank you, Steve. If everybody maybe want to unmute themselves and give them a clap, that would be good. Thank you so much.
Absolutely, yes, and thank you very much for really enjoyed all the submissions, and I suppose as an architect, I particularly enjoyed the bullet center. So thank you all.
Huh?
Yes, great. Thank you. Thank you very much for attending, everybody, and hopefully see you either at the show and tell or online again for the other seminars next year. Great.
All right.
Thank you. Thank you.